So the first thing we're asked to do in lesson 10 is to graph x minus 2 cubed, x minus 5 cubed, and x minus 2 cubed, x minus 2 to the 5th, and x minus 2 to the 7th. Now, something you should recognize that's happening is I'm dealing with odd exponents, and that minus 2 is doing a brutal job on some variable for my polynomial. What variable am I manipulating? Or what part of the graph is that going to affect? What variable is minus 2 to the 3, or minus 2 to the 5, or minus 2 to the 7? How's that going to show up? Please graph these three and try and squeeze them on the graph that's presented. So what's different about these graphs? Well, they all have a squiggle or a slide through the x value of 2, but the y-intercepts are all different. The first graph I've put on there is the 128 graph, where the y-intercept is down at minus 128. Then the next graph has a y-intercept that comes in at about minus 32, and then squiggles. And then the other one has a y-intercept that is at minus 8 and squiggles. So if I take a look at my graphs, I've got a difference in the y-intercept value, and I've also got a difference on the top in terms of how quickly it moves up. So we could think about how this might be interpreted from our first unit. So if I take a look at the graphs of the squared ones, or squared 4s and 6s, I notice that the graphs all touch at x equals 2. Those are tangents or local maximums or minimums. So as the multiplicity of the 0 increases through the even numbers, how would you describe what's happening to the graph? So we've got that language. Same inflection point for the first set of graphs, same tangent point for the second set of graphs, and now we get to see how that affects our graphs in the world of not knowing what equation we had. Let's turn the page. So some rules that probably sound familiar. If I have even multiplicity 2, 4, or 6, I'm going to get tangents or maximums at the points on the graph. If I have odd multiplicities greater than 1, 3, 5, 7, or etc., I'm going to have that point of inflection or the slide. So we want to take a look at what's happening to our graphs. We've got 4 different graphs to look at. And I just want to start first with identifying whether they're odd or even multiplicities. So take a look at your graphs. Are they odds or evens? You can simply use an O or an E. I'm going to see if all the volleyball guys have left. Just wondering about the question, can we call these or view these as vertical stretches? Does that help us think about our first unit? We're changing the y-intercepts, the x-intercepts are staying the same. Is that a vertical stretch? Let's go back to those multiplicities. So we were looking to identify whether we had single, double, or triples. So when I have touches or tangents, like here and here, those are called evens. So those are even multiplicities. Here's another even. This one on this side is a single that has a multiplicity of 1. I know that for sure. It's going straight through. Here I've got some singles going straight through. Here I've got a squiggle or a slide. This counts as an odd. Now what's this one? This one didn't go through. It actually is an even. It goes up, or it comes down and then goes up. It's an even multiplicity. Here is an odd multiplicity, pardon me, not an odd, a single, because it just goes straight through. So let's see if we can look at the analysis. In each case, state the number of distinct zeros and the possible multiplicities of each zero. So the number of distinct zeros, how many distinct x-intercepts are there for number 1, or I? There are 2 distinct, oh, I forgot to label this one. What's this one? That's a slide or a squiggle, which is an odd. So that one's an odd. Looking at 1, I've got 2 distinct roots, 2 roots. The first root is even, so at position A, I've got an even root, so it's 2, 4, 6 in terms of multiplicity. At position B, I have an odd root, so it's 3, 5, 7. In graph 2, or II, I have 3 distinct roots, 3 roots. And going through maybe a few more letters of the alphabet, so that was A, B. I'll go C, A, B, C, D, E. C is a single root. C and E are single roots, so they have multiplicity of 1. D is an even root. D is an even root, which is multiplicity of 2, 4, or 6. On triple I, I've got 3 distinct roots, F, G, and H. F and G are both even. So I've got 3 roots. F and G are both even, so that means they're 2, 4, or 6 or higher. H is a single, so it has a multiplicity of only 1. And then I've got IV left. IV also had 3 distinct roots, and I'm on letters I, J, K. So for IV, which is over here, I and J are single roots. There are 3 distinct roots. I and J have a multiplicity of 1, and K has an odd multiplicity. So that's 3, 5, 7. Now where could I get degree 8? Remember degree 8, my multiplicities have to have a potential of adding to 8. And as I make some distinctions, just talking through a couple of them, looking at I can have a root of 6 and a root of 3. That's 9. That's not enough. Here in double I can have a root that has a multiplicity of 6 plus 2 with a single one. So graph 2 could be degree 8. So graph II could be degree 8. Graph 3, I had 2 of 2, 4, or 6. So I could have 1 at 4 and 1 at 2, that's 6, and then that's degree 7, so that doesn't work. In graph IV, I can get up to 7 and then pick 2 more, that's 9. So it turns out there's only one answer for degree 8, and that's double I. In which of the graphs is the leading coefficient positive? Now, what's the distinction for the leading coefficient being positive? The leading coefficient being positive should show the right arm increasing. And the right arm increasing only happens in triple I and IV. So we have to figure out ways of dealing with this without a calculator, although many things you can check with a calculator. What am I looking for? I'm looking for the degree. I have a degree that's 6, so I have an even degree, and I have a negative leading exponent. And the pattern that I've seen is that when I'm even and I have a negative leading exponent, I'm going to start and end on the lower quadrants. So I need to have x-intercepts at 0, at 1, and 4 of them at 1, and at -4 or +4, pardon me, the opposite side. So change the signs. So I have to start and stop here. What is that graph going to look like? So my multiplicity of 4 was a touch or a bounce. It bounced up. I went through the x-intercept of 0 once and 4 once. And you can check that using your calculator. We're looking for the lowest degree here, so we get to count our x-intercepts at their lowest value. So A comes in with a 2, D comes in with a 1, F comes in with a 1, which is degree 4. And I'm going to have real and equal roots only at A. A has real and equal roots. The graph beside is almost as nice. I have 2 squiggles or 2 slides. They count as degree 3. The lowest possible degree of my polynomial is 6. And P and S will have 2 distinct roots that are equal. All right, some things you should have learned in graphing. When the degree is even, and I have a positive coefficient, I will start in the upper left-hand quadrant and end in the upper right-hand quadrant. When I have a negative leading coefficient, I will start in the upper left-hand quadrant and descend into the lower right-hand quadrant. And now I've got to deal with my multiplicities and crossing and stuff. So let's see what those graphs will look like. Just talking through my graphs, I wrote the multiplicities on top, 1, 2, 2, 5 for the first one, 1, 1, 3, 4 with the appropriate starting and ending positions. Go through, touch, touch, slide. On this one, I start in the top, go through, slide, touch, and come back down. That's it for this lesson. Hope we can have some